Okay, so it's time to begin the last talk for today. The speaker is William Johnson. I guess he needs no introduction, but anyway, he's a distinguished professor at Texas A&M University, and today he's going to tell us about some 20-plus-year-old problems about Banach spaces and operators in them.
Thank you. This week, my wife and I will have been married 50 years, and so I'd like to begin by thanking her for agreeing to defer the celebration of this very happy occasion so that I could give this talk. So here is the title of the talk as well as a subtitle, and maybe I should explain a little bit. Just after this millennium started, it occurred to me that it would be a good time to look at problems in Banach space theory and problems about operators on Banach spaces that were of interest in the 1970s and early 1980s that maybe we could attack with recently developed tools and make some progress on. That's the official record. Now, those of you who are a little bit older will appreciate that I was approaching my 60th year, and I was finding it easier to remember things from 20 years earlier than why I had gone from the kitchen back to the bedroom. So fortunately, I'm blessed to have a lot of colleagues to help in this project. And so I will give a few instances of a few problems and solutions of a few problems that have been accomplished this millennium. And each topic I will address is independent of all the other ones, technically. So if you don't pay attention to one, you can pick up at the next one. You might find a common thread or two going through. I wanted to begin with this one, which is one of the oldest one, because Ted Odell was my first PhD student who unfortunately died much too early. There's one simple definition that was already made in the preceding talk. The isomorphism constant between two Banach spaces is denoted this way. You look at the infimum, already a typographical error, infimum of norm t times norm t inverse over all isomorphisms from x on to y. And then if you look at all the Banach spaces that are isomorphic to a given Banach space, you have the diameter of that isomorphism class given this way. Of course, whether this is finite or infinite is not clear a priori. However, suppose you could think about a finite dimensional Banach space, x has dimension n, then it's isomorphic to all other finite n-dimensional Banach spaces, and you can ask about the diameter of that. This is the diameter of the Minkowski compactum. This is a famous problem, and this was solved finally in the early 1980s by Fima Glushkin, who proved that this diameter was of order n. For infinite dimensional spaces, it's natural to guess that the answer is infinity, as you let n go to infinity and you get this. And this was formally raised by Juan Jorge Schaefer in 1976, although he didn't claim any originality for this problem. He knew it had been around, but he put it in his book. That is the diameter of the isomorphism class of an arbitrary infinite dimensional space infinite. Nothing was done on this after he wrote his book, and then Vladimir Guerari, the late Vladimir Guerari, repopularized this in the late 1990s. And he pointed out that for most of the common Banach spaces and classes of Banach spaces, the diameter of its isomorphism class indeed is infinity. And we put a small argument, Ted and I, into the introduction of our paper that explained this phenomena. If you take an infinite dimensional Banach space, take an arbitrary finite dimensional subspace E, and take a closed complement to it, then that's a good topological direct sum, so you can renorm the space to make the projection onto E norm 1. And then you can renorm E any way you want to make it as bad as an n-dimensional space can be. So this means that if d of x is finite, then every finite dimensional Banach space is C isomorphic to a C complemented subspace of E, where C is this diameter of the isomorphism class. So this means that X can't have any good property that's defined in a finite dimensional way. It can't have type, it can't have cotype, it can't be isomorphic to a uniformly convex space, and it can't be any of the classical spaces. So this is an interesting beginning to the problem, but it's also misleading because the solution of the problem has nothing to do with this. That seems to take you a long way. So what Odell and I did in 2005 is give an affirmative answer to this question when the Banach space is separable and infinite dimensional. So in order to do that, we introduced this concept. It's an obvious concept, but really hadn't been studied. It's called a Banach space K-elastic, where K is just a numerical parameter, provided every isomorphic image of the Banach space is K-isomorphic to a subspace of X. So and elastic just means K-elastic for some constant K. So what does that mean? You take X, and you take an equivalent renorming of X to try to pull it way away from X. And elastic says you can't do that. It snaps back, and this renorming of X actually sits inside of X up to this constant K. So the main theorem we proved is that if you have a separable Banach space so that every isomorphic of X is K-elastic, where K is some constant, then X has to be finite dimensional. And this immediately gives the answer to the Schaefer question in the case where X is a separable Banach space. Now, what are the examples of elastic Banach spaces? Well, it's a classical one. One of the very early results in Banach space theory, proved in the 1920s by Mazur, a student of Banach, is that the continuous functions on the unit interval is a universal separable Banach space. Every Banach space is separable Banach space is isometrically isomorphic to a subspace of this one, and therefore this space is one elastic. Now, Ted and I guessed that this was the only way a space could be elastic, is for it to be universal and therefore contain some subspace isomorphic to C01. So any Banach space that contains a K isomorphic of C01 is then K elastic, okay? And the proof that we gave could be streamlined a lot if we had been able to prove that. We weren't able to prove that. So we had to prove something weaker using Bourgain's L-infinity index theory. One of the first steps of the proof was to show that, using Bourgain's theory, that we could, that a separable elastic Banach space contains a subspace that's isomorphic to this much smaller space in C01 of C0. Well, this comes to the second reason that I wanted to talk about this particular example of an old problem. My third PhD student, Dale Alsbach, with Bunyamin Sari, answered this conjecture of Odell and myself. They verified it. And they did this by creating a more complicated version of Bourgain's L-infinity index. And of course, we were hoping to simplify our proof of solving the Schaefer's problem. Actually, if you use their proof and input it and then simplify our proof, it's 10 times more complicated than our proof. But still, it's a very nice result. And fortunately, just a couple of years ago, Kevin Beanland and Ryan Causey were able to simplify this proof of Alsbach and Sari by interjecting some more descriptive set theory into it. And I feel confident that this index will have an impact down the road. If you go to the non-separable case, Schaefer's problem is wide open. There do exist elastic Banach spaces of every density character under the generalized continuum hypothesis. So that's one step that you might want in order to get started. But all the other tools that were available in the separable case for attacking the problem just don't go anywhere. The only positive result was done by Gilles Godefroy in 2010. He showed under Martin's axiom, you can get an affirmative answer, at least for subspaces of L-infinity. But that's a bare beginning. So the second old problem I want to discuss involves another one of my PhD students, a much more recent one, Detlan Dosef, and my very frequent collaborator, Gidon Shekman, whose name will come up a few times in this talk. And in this, we were looking at commutators in the bounded linear operators on classical Banach spaces, and particularly in little L1, in little L infinity, and on LP of the unit interval for, say, P finite. So no matter what area of mathematics you're interested in, commutators come up. And in Banach algebra theory, you're interested in derivations on them, and so they arise in a very natural way. Now, if you look at a finite dimensional Banach space, there's a very classical and beautiful characterization of the commutators in L of x. So these are just n by n matrices, and these are the matrices that are of trace 0. So it's a theorem in linear algebra, of course, because all the norms are equivalent here. It doesn't really matter. But I have a question. Has anyone in the audience ever taught this theorem in linear algebra? Please raise your hand or speak out if you have. I see, let me see, 0 hands went up. Why do we not teach this theorem? It can be taught in a second course in linear algebra to undergraduates. Absolutely beautiful and useful theorem, but it seems like no one teaches it. Now, if you go to a general Banach algebra, one with identity is only algebras I'll consider, there's only one obstruction to an operator, to an element of the Banach algebra being a commutator, and this was discovered by Wintner 70 years ago. So he proved that the identity operator cannot be a commutator of two bounded linear operators. Well, and since this works for Banach algebras, if you're in a Banach algebra and you mod out an ideal, you get a Banach algebra. So this says that if you take a non-zero multiple of the identity, a non-zero scalar operator, and perturb it by an operator in a proper ideal, then you can't have a commutator. So this is an obstruction, and the only one we know. Now let me give a proof, not Wintner's proof, but Wieland's beautiful proof that the identity is not a commutator in a Banach algebra. So let's assume the identity is a commutator of A and B. You give a very trivial induction to show this identity, and notice that if A to the n is 0, so is A to the n minus 1 from this formula. Therefore, A cannot be a nilpotent operator. Well, then the norm of A to the n is less than or equal to the norm of A to the n minus 1 times the norm of A. So that gives us inequality. And you know that now that A to the n minus 1 is not 0, so you divide through by it, and you get the result. A breakthrough was made in 1965 by Carl Pearcey and Arlen Brown after the problem of classifying the commutators on L of H, where H is separable infinite dimensional Hilbert space, was popularized by Helmholtz some 10 years earlier. There's a lot of study of this, and they were able to show that the Wintner obstruction to being a commutator is the only obstruction in this particular space, and the bounded operators on a Hilbert space. Now, research continued in this direction, but it took 7 years before Constantine Apostel was able to prove that the same characterization works in the bounded linear operators on the little LP spaces in the reflexive range. And the reason for this is that the basis for little LP, it looks very much like an orthonormal basis. It has many of the properties of an orthonormal basis, and so he was able to get rid of the Hilbert space operator theory and the Brown and Pearcey theorem in order to do this. Now, lack of reflexivity in C0 prevented him from doing it initially, but he realized that a year later that he could also cover that case. And here the key thing is that the basis for C0 also looks a lot like an orthonormal basis, but it has a property that, notice that one is missing here, that the basis for L1 lacks, and that's that it's a shrinking basis, meaning that the biorthogonal functionals form a basis for the dual space. Now that's wrong in L1, so he wasn't able to do the case of little L1. But he did give some information about commutators and the bounded operators on L1, also on L infinity, also on the continuous functions on the unit interval. He didn't do much on the bounded operators on big LP of the unit interval, but a student of Pearcey, Schneeberger, did, showed, for example, that the compact operators are commutators, at least for P in the reflexive range. But nothing else was really done, and research in this direction kind of petered out until 2009, when Dosef in his dissertation solved this problem for little L1, giving the same characterization, and this led to renewed interest in this particular topic. So what he was able to do is show that, well, it's true that the lack of shrinkingness of the basis of little L1 causes problems. However, if you're given an operator, you can change the basis for little L1 to another basis that's equivalent to it, more well adapted to that operator, and then the arguments can be made to go through. So it's a very nice thing. Now, the obstruction to being a commutator is being of the form non-zero multiple of the identity plus something in a proper ideal. Now, you have to understand something about ideals in order to begin to investigate this problem on the space. Well, you don't have to understand something about all ideals, but about the maximal ideals, right? Every ideal is contained in the maximal ideal. And since the invertible elements in a Banach algebra are open, the maximal ideals are automatically closed. So you just have to look at the maximal ideals. Well, this is pretty easy when you're dealing in these simple spaces. Because the compact operators form the unique maximal ideal. In fact, they're the only closed ideal. They're also the smallest ideal. However, if you go to a space like L infinity, now it also has a unique maximal ideal, but it's a set of weakly compact operators, not compact operators. So this is quite a bit larger. And, but Dosef and I were able to prove not too long after he had done the L1 theorem that you could then classify the commutators in this space as the same way. So the Wintner obstruction is still the only obstruction in this space. Now, let me say something about approaches to this problem. Suppose you are looking at a general Banach space X, and let's assume for simplicity it has just one maximal ideal, not a big deal. And you want to classify the commutators as being all the operators that aren't excluded by the Wintner condition. So there are two steps. You first have to show that everything in the maximal ideal is a commutator, and then you have to show that these other operators are commutators if they're not excluded by the Wintner condition. So these actually breaks naturally this way. Now, in the first step, they all, in every case in which there's a solution, you just rely on proving on this particular fact. So this is a general fact. And then what you have to do is show that the operators in the maximal ideal satisfy this condition. And that's pretty easy when the maximal ideals consist of compact operators. The smallness condition is not really very much, right? Because you have a compact operator, if you pass to a finite codimensional subspace, that operator will have arbitrarily small norm like this. Given any epsilon, there's a finite codimensional subspace so that you have this. So this is not such a big condition. But in other spaces, that's wrong, and so it turns out to be quite a bit harder. Now, even this easy case of where the maximal ideal is a compact operator depends on the fact that the underlying space has something called a Pelchinski decomposition, which means it's isomorphic to the LP direct sum of itself infinitely many times, and P can be anything between 1 and infinity, or it can be the C0 sum. So the reason this makes it easy is that this gives you right and left shifts of infinite multiplicity. And once you have these kinds of shifts of infinite multiplicity, you can build a lot of operators. On the other hand, if you look at a rigid Banach space, such as those considered by Spiros and Richard, you have no such decomposition. You can't even get started on this particular problem. There, you have nothing like a shift. So what is really true and not too hard to prove, that if X is any Banach space that has a Pelchinski decomposition, then every compact operator is a commutator. So let's assume that the space has a Pelchinski decomposition and a unique maximal ideal. And if you want to do step 2, again, anytime we were able to do anything, it depends on this particular theorem. Now, so if you look at this theorem, the nice thing about it is that it means that to solve the problem of determining what the commutators are, you really don't have to do any operator theory. All the operator theory is built into doing this, but you still have to prove some structural theorems about Banach spaces and how operators act on them. And this was done by enlisting the aid of Gideon Sheckman and for the spaces LP on the unit interval. And the problem here is that the maximal ideal is a very complicated set of operators, and it's just described as being all operators that are not isomorphism when restricted to subspaces of LP that are isomorphic to LP. Here's a wild conjecture, that the only obstruction to being a commutator in L of X is the Wintner obstruction. We know that this is wrong because of Matthew Tarbert, a student of Hayden's, who built an example one step past the example that Richard and Spiros talked about, that has a property that every bounded linear operator is the form scalar plus a multiple of a particular strictly singular operator S plus a compact operator. The strictly singular operator S is not compact, but its square is compact. And it's very, very easy then, just using the definition of commutator, to show that S cannot be a commutator. So here's a nice open problem. For spaces that don't have a Pelchinski decomposition, are compact operators commutators? Are compact operators commutators on the Argyros-Hayden space? Don't know. This is open for every infinite dimensional space, including Hilbert space, where it's a very famous problem. Is every compact operator not only a commutator, but a commutator of two compact operators? Well, I don't really believe this is a Hilbert space problem. I think the problem probably has the same answer for any spaces that has a Pelchinski decomposition. So the next topic I want to talk about is completely independent of the last one, but it still involves ideals and the bounded operators on LP. And this is the most recent of the things I'll talk about. In fact, this paper is just now written, and as soon as we finish the proofreading, we'll have it available, joint with Gilles Pizier and Gideon Sheckman. Now, if you're studying commutators, all you care about are maximal ideals in the bounded operators on the space. But if you want to understand something about the Banach algebra structure, you have to understand something about all ideals, because you want to understand the homomorphisms. The homomorphisms are multiplicative bounded linear operators, and their kernels are, of course, the closed ideals. So you have to understand something about the closed ideals. Now, this is very easy if you're talking about little LP, because the only closed ideal is the space of compact operators, as I mentioned. But for capital LP of the unit interval, things are rather more complicated. And it's useful to make a distinction between two kinds of ideals. Call an ideal small if it's contained in the strictly singular operators. I've repeated the definition of strictly singular here, and just say one more thing about them. Strictly singular operators are not necessarily compact, but they have exactly the same spectral theory as compact operators and the same perturbation theory. In fact, this is why Cato introduced this class of operators a long time ago. And something's not small, let's call it large. Now, how do you construct ideals? First, how do you construct large ideals? Very simple You take a projection from the Banach space onto an infinite dimensional subspace, okay, and look at the ideal generated. This cannot be strictly singular because it's an isomorphism on the complemented subspace Y. And as long as the ideal generated by this one operator is not the whole space, it's an ideal. Ideal, I mean a proper ideal, of course. Now, if y is isomorphic to y plus y, then the operators that factor through y is closed under addition. It obviously has the ideal property of multiplication. So then why will this thing I described, the ideal generated by y, will just be the closure of all the operators on x to x that factor through the subspace y. And this will be proper as long as x is not isomorphic to a complemented subspace of y. So constructing ideals that are large in L of x means finding complemented subspaces that are not isomorphic to the whole space and in fact don't contain complemented copies of the whole space. So this was, a lot was done way back in 1975. Sheckman proved that the bounded operators on LP in the reflexive range has at least countably many ideals by constructing countably many isomorphically different complemented subspaces that satisfy these extra conditions. And then a few years later, along with Bourgain and Rosenthal, they improved Aleph 0 to Aleph 1. Now we're still waiting for what happens at the Aleph 2 or the continuum. So if you're in ZFC, we really don't know how many large ideals there are or how many complemented subspaces are. Of course, there can't be more than the continuum because LP is a separable Banach space. Can't be more than a continuum of complemented subspaces. We don't know whether it can be more than a continuum of large ideals. What about small ideals? Well, this took longer, and as a result of intensive work during this millennium, Schlumprecht and Sachs eventually proved just this year that the bounded operators on LP in the reflexive range have infinitely many, a continuum in fact, of closed small ideals. And this was a problem raised by Peach in his 1978 book on operator ideals, whether there are infinitely many. How many there are is still open, whether there are more than a continuum. So, of course, LP is a separable space, so it only has up to isomorphism a continuum of closed subspaces. But we're talking about the Banach space L of LP, which is highly non-separable, so we really don't know what's going on there. Now, back when Peach wrote his book, the case of L1 was very different. The only ideals known were two small ones, compact and strictly singular, and two large ones, the operators that factor through the complemented subspace little L1, and a unique maximal ideal that was described by Inflow and Starbird. So it's not so hard to write down candidates for ideals. The difficulty is to prove that they're different. For example, suppose you take all the operators on capital L1 that factor through capital LP. It turns out when you close this up, you get the set of weakly compact operators. And weakly compact is the same as strictly singular on L1 because of L1 has something called the Dunford-Pettis property. So what we did is construct a continuum of closed small ideals in the bounded operators on L1, which solved actually one of the main problems that Peach raised about closed operator ideals. But whether there are more than two large ideals, we don't know. And of course, this is connected, as I've already said, to the well-known problem whether every complemented subspace, infinite dimensional of capital L1 is isomorphic either to little L1 or the whole space. No more about this topic, because I'm just going to introduce a commercial here that I'm going to say more about this particular paper next week. So this is the first of two papers I will mention with Moret and Sheckman. This is also kind of has to do with the lecture that Asaf Naor will give tomorrow morning when he begins to speak about the REBA program. So script L1, or script LP spaces, were defined already in the preceding talk, but let me just repeat the definition. Here I give it for L1, but you take, in the separable case, you take an increasing sequence of finite dimensional subspaces, and you demand that they're uniformly isomorphic to the LP space of its dimension. Now, if P is in, say, finite, and you demand that they're isometrically isomorphic, what you get from Kakakani type representation theorems is that you're just building either little LP, you're just building LP of a separable measure. It's much different for P equals infinity, but I won't talk about that case. Now, a very interesting fact proved by Reba is that if you look at nonlinear equivalents of Banach spaces, and in this case I'm talking about nonlinear equivalence, meaning you have a uniformly continuous map with uniformly continuous inverse, but not linear, that the script L1 space, the script LP spaces for P in the reflexes range are preserved. That is, if you have a script LP space and it's uniformly homeomorphic to another space, that other space is script LP. Now, he wasn't able to do anything for the P equals infinity and P equals 1 cases because of the lack of reflexivity, but in this paper of Heinrich and Mankiewicz that came later, they gave maybe a simpler proof of what Reba did in the reflexive range, and they also were able to prove that script L infinity spaces are preserved under uniform homeomorphisms. However, they weren't able to do the case of script L1 spaces, and this is what Moret and Sheckman and I did in this paper. Subsequent to that, Nigel Calton showed that there exist two separable script L1 spaces that are uniformly homeomorphic, but they are not isomorphic as Banach spaces. So they're within these class of spaces, it's very important you really switch the types of the spaces. Now there's a problem that I think everyone can identify with. Suppose you have a mapping between two objects that has a certain property. So my property is bounded linear operator, but your property might be different. And suppose it emits a factorization through another object where the factorization maps have a weaker property, in this case Lipschitz. So this is like bounded linear operator is same as saying a linear operator that's Lipschitz. So you just throw away linearity, but you keep the Lipschitz condition. Then what more do you need to guarantee that you get a bounded linear factorization through Z? So this comes up in topology, geometry, this kind of question, as well as functional analysis. Now, in this particular context, we know that something else is needed because the identity on continuous functions on the unit interval factors through C0, but certainly does not linearly factor through C0. So this is what we proved. It looks like a modest result, but it gets what we need. Suppose X and Y are finite dimensional. Well, Y doesn't have to be finite dimensional. Reflexive is enough, or Radon-Nikodym, which I won't bother defining, is enough. But we care about the case of finite dimensional ones. And suppose you have a linear operator from X into some Banach to this Y. And suppose it has this Lipschitz factorization through some Banach space Z. Then you get a linear factorization with good estimate through, not Z, unfortunately, but through L infinity, through the formal identity mapping that takes L infinity of Z to L1 of Z. Remember, we're talking about L1 is on the unit interval, L infinity is on the unit interval, so the injection goes from L infinity to L1 is the contractive injection. So you get this. Well, that doesn't get what we want. However, if Z is L1, then so is L1 of Z. L1 of L1 is an L1, and that passes to this context. And so that means that, in this case, Z factors through a script L1 space. Well, once you have this preliminary theorem, then you begin to use your bag of tools that have been around for a while, and you can give an answer to this problem. Here is a second paper of Moret and Sheckman and myself that I wanted to mention. And this also harkens back to the preceding talk. You study properties of Banach spaces very often by looking at weakly null normalized sequences and passing to subsequences that have good properties. So the first theorem in this direction was done by Mazur, that if you have a weakly null normalized sequence in a Banach space, there's a subsequence that forms a Schauder basis for its closed linear span. That's a very important and well-used theorem. Now, in 1964, Pelczynski said, well, you know, maybe you can do better than the Mazur's theorem, and you can get a subsequence that is not only a Schauder basis, but it's an unconditional Schauder basis, where the expansion not only converges, it converges unconditionally. Now, that's very important because Banach spaces that have unconditional bases carry much, much more structure. It's very easy to describe reflexivity for a subspace, for example, much easier than general Banach spaces. Well, a counterexample was built by Moray and Rosenthal in 1977. Now, Gowers and Moray, 15 years later, constructed a Banach space, so there were no unconditional sequences in it at all. So forget about Moray and Rosenthal, right? No, that's wrong. You should never forget about the roots, and this is one example of that, because the examples that Moray and Rosenthal did were actually very classical Banach spaces, continuous functions on just countable compact sets. And these spaces have the property that every subspace has unconditional sequence, not just an unconditional sequence, but even C0, which is unconditional as it gets. And the way they were proving it is a very nice strategy. They built a weakly null normalized sequence in these spaces so that every subsequence reproduces not the unconditional basis for C0, that's fine, but a special conditional basis for Z0 called the summing basis. C0 has its natural unconditional basis, but also has a very good conditional basis. And they ask in this paper whether every weakly null normalized sequence in capital L1 has an unconditional subsequence. Now, if you look at capital LP for P in the reflexive ring, it already has an unconditional basis, and so it's very easy that every weakly null normalized sequence has a subsequence that's essentially a block basis of that, and so it's unconditional. But L1 has no unconditional basis. It doesn't even embed into a space with unconditional basis, so they didn't know, they weren't able to build an example. But this is what Moray and Sheckman and I did in this paper. And we followed the same kind of strategy as Moray and Rosenthal by finding a nice conditional basis for L1, and one's just staring at you, it's the Haar wavelet basis. And so we constructed a weakly null normalized sequence so that every subsequence reproduces on blocks this conditional Haar basis. And there was kind of an added little twist here, is it really didn't depend. So if you express it this way, the proof actually worked for many RI spaces where you don't worry about the Haar basis, whether it's conditional or unconditional, you still get the reproduction thing. Now, I'm not going to leave weakly null normalized sequences, but I'm going to go to a completely different topic and two papers with another one of my recent students, Bento Zheng, that appears two different places. So I did say that Banach spaces have an unconditional basis, have much nicer structure than the general Banach space. Okay, so if your Banach space is presented as a subspace of a space with unconditional basis, that's well and good. But how do you tell, just looking at this Banach space itself, whether you can embed it into such a space? So this is an annoying problem that goes back at least to the 1970s. Now, there are some things that were known or improved during the 70s. Suppose the Banach space has an unconditional finite dimensional decomposition or something a little weaker, unconditional expansion of the identity. Now, this is an approximation condition. It means that you have finite rank operators so that their sum converges in the strong operator topology to the identity. And moreover, that's just would be called the bounded approximation problem, but moreover, this series converges unconditionally, pointwise. So that's a strong condition, a strong approximation condition. Then you get a positive result. The problem with this is that if you get past Hilbert space, and I get past Hilbert space, and you look at any of the other LP spaces, they all have subspaces failing the approximation property. So any reasonable Banach space other than Hilbert space probably has a subspace failing the approximation property, so you can't use it here. Now, the only obvious invariant for subspaces of spaces with unconditional basis is that every weakly null normalized sequence has an unconditional subsequence. So this is another property that was investigated quite a bit. And combining stuff that I did and Odell did, a quotient of a space with shrinking unconditional basis has this property. And quotients tend to look different from subspaces, but still. Also, Moshe Feder, again, introducing the approximation property, says, well, if you have a quotient, a reflexive quotient of a space with shrinking unconditional basis, then as long as it has the approximation property, you can actually prove that it has this stronger approximation property I mentioned on the preceding slide of having unconditional expansion of identity, and therefore embeds into a space with unconditional basis. So there are these two problems. Give this, the first one I already mentioned, the second one I just implicitly talked about. Is this a sufficient condition to have an embedding? Let me just say, shrinking is in the second one is really important, because if a space has unconditional basis not shrinking, then it has a complemented subspace isomorphic to little L1, and every separable Banach space is a quotient of it, and so you can't say anything. So a few things were done. But what Bento and I did is give affirmative answers to these questions. Well, I don't know what it means to say an affirmative answer here. What it really means is that we gave a criterion, as I'll say in a moment, and gave an affirmative answer to 2 always in our second paper, and for spaces have separable dual in the first one. So the way that we combine this, at least in the reflexive case, is to start with a reflexive separable Banach space and give a long list of equivalents. So brace yourself, please. Yeah, well, don't read this. Except for B, that's where we're headed. Now, what are C, D, E, F, G, H, I? Well, tell me a possible condition that's equivalent to X embedding into a space with unconditional basis. It's listed here. So anything that might be equivalent is equivalent. But the connection is the UTP, which turns out to be a self-dual property. So what is the UTP? Unconditional tree property introduced by Odell and Schlumprecht. So you take a weakly null tree. What does weakly null tree mean? Well, tree means tree, but weakly null just means order is a sequence and it goes weakly to 0. It doesn't matter how you order it. And unconditional tree property says that if you have an infinitely branching tree, so every node has countably infinitely many successors, then if you have a weakly null infinitely branching tree, then it automatically has a branch that's unconditional. Okay? So it's very much like every weakly null normalized sequence has an unconditional subsequence, right? Except it's a tree version of it, and it's stronger than the subsequence version of it. It's just a strengthening of it. But the weaker property, that every weakly null normalized sequence has an unconditional subsequence, is not enough. We give an example, which is actually based on another example of Odell and Schlumprecht in this paper. So it uses quite a lot. And that's all I'll say about it. Now, I do want to say something, and I'm running out of time, so I'm skipping to one of my favorites, and also to my second commercial, which is Math Overflow. I'm a bit of a Math Overflow junkie. And this question was raised by Nasseri on Math Overflow, and it got quickly 2 close votes. Well, okay, maybe, but it took a couple of years to resolve this. Nasseri and I enlisted I did what I always do. When I couldn't solve something, I go consult with Sheckman, he consulted with Tomek Cox, who is was at that time a PhD student of Keith Ball, who's now a postdoc at Princeton. So the reason it got closed votes is that on any separable infinite dimensional space, it's easy to build a compact operator that has dense range. And of course, compact operators can't be surjective on infinite dimensional spaces. But they have separable ranges, so it doesn't lead anywhere. And on non-separable spaces, every dense range operator doesn't have to be surjective. It can be surjective on certain spaces. And even experts don't know that, but Spiros knows this very well. I asked him, and he pointed me to this example, one of the many great examples that he and his students did. So this looked like a non-trivial problem, but it's also equivalent to a problem about Tiberian operators on L1. So this is a deceptively simple concept. Tiberian operator just means a condition on the second adjoint. However, a whole book has been written about this concept by Gonzalez and Martinez-Avion. And in there, they study, among other things, Tiberian operators on L1 that has this nice equivalence, of which this last one is the main one. So this last one says that the operator has to be an isomorphism, but only on sets of vectors which have small support. Now, if you have a what's the connection, though, between Tiberian operators on L1 and dense range surjective operators on L infinity? Well, it's pretty obvious from the definition that if T is one-to-one Tiberian, the second adjoint is also one-to-one. Right? That's not trivial. So if you have a Tiberian operator on L1 that's one-to-one, but it doesn't have closed range, then the adjoint has to have dense range, because dense range for T star is the same as one-to-one for T double star. And closed range for T is the same as closed range for T star. So this would be a dense range operator on capital L infinity that's not surjective. What does that have to do with little L infinity? Well, it's been known for 60 years that these two spaces are isomorphic. So this is the connection between the series problem and Tiberian operator problems. And even without knowing the answer, you can do some arguments to show that they're equivalent. Now, the series problem is not 20 years old, of course. Math overflow is not that old. However, one of the open problems that appears in this book was raised by Weiss and Wolff back in 1984, which was more than 20 years ago. Is there a Tiberian operator on L1 whose kernel is infinite dimensional? Now, it turns out that if you can solve this old problem, then you can play around and get a perturbation that solves this other problem. So in other words, whether you have a dense range non-surjective operator on L infinity, which is non-separable space, is really a question about getting a Tiberian operator with infinite dimensional kernel on the separable space. So this non-separable problem is not really a non-separable problem. So I repeated the equivalence of Tiberian for operators defined on L1 in the book. And it turns out that this infinite dimensional condition here has a known finite dimensional analog. So here's the CS theorem. CS stands for computer science. All of these people are connected to computer science or are in computer science departments. If you don't like computer science, CS stands for compressed sensing, because it's the same in here. Here's what they prove, which is an exact analog, finite dimensional analog of this. You can map L1n to L1m with a nice operator. It's norm 1. That's an isomorphism on vectors which have supported on a set of measure 1 over 400. All right? And the kernel is infinite dimensional. Well, not infinite dimensional, that'd be difficult, but it has dimension at least 1/4 the dimension of the whole space. So that's a finite dimensional analog of this. A very special case of their theorem, by the way. Then you can use some tools in Banach space theory, including ultraproducts and some other things, in order to get an operator on capital L1 that satisfies this condition with exactly the same constants. Well, if it's the same constants, it can't be that difficult, right? So there's a non-surjective Tiberian operator on L1 that has dense range, and it can either be one-to-one or have infinite dimensional kernel. And therefore, you get an answer to the necessary question as well. Now, but the conclusion from the proof is one of the main reasons I wanted to include this example. You can apply computer science to non-separable Banach space theory. I know some applications going the other way, but I don't have time to talk about them, so thank you very much.
Okay, thank you very much. Maybe we have time for some very quick question or comment. Okay, so in case you have any not so quick questions or comments, I'm sure we can discuss later. So thank you very much.